Okay, so we're done with the PowerPoint. We're actually onto the board here, and we're going to do an analysis of what happens when the 45,000 nanosecond adjustment has been made, and the two clocks, because of that pre-launch adjustment, the two clocks are actually synced in both directions. Each direction is happy, and each clock is actually proceeding at the same rate. Now we actually send that satellite in orbit. We impart a velocity on it, and it's a fast enough velocity for it to stay in orbit, which would convert to enough velocity for a discrepancy of 7,000 nanoseconds slower from the position of the Earth. But the interesting thing is if we are to, and what I'm going to do is I'm going to start out by giving you the theory that I wrote up in 2008. And then we can talk about how that might be different than what we've got right now. In 2008, what I said was this would be a perfect test for Einstein's symmetrical reciprocal clock slowing effect that would actually be happening to each clock simultaneously from each other's perspective. Again, equal but the same instead of equal but opposite. And because what I said was, if you're on the Earth, and I've got Colorado as an example here because you could be driving around the streets of Colorado with a GPS receiver in your car, and you also wouldn't be too far away from one of the ground control station clocks that communicates with the satellite. So this would be a good location where Colorado's a good town where there would be communications going in both directions. So in this particular case, the satellite starts moving. So from the ground, then I would see this clock suddenly traveling with a velocity, and its clock would slow down by 7,000 nanoseconds per day. My argument was, from the perspective of the satellite, that means the satellite would read the ground clock is also going 7,000 nanoseconds per day slower than itself, right? The problem arises when we make some sort of an adjustment to compensate for the velocity. If Einstein is correct and we have this mutual symmetrical time slowdown from each perspective simultaneously, it's impossible to do a two-way syncing system. It's impossible to make any kind of adjustment on the satellite clock so that it would be just right from the perspective of both simultaneously. Because again, if this is running 7,000 nanoseconds per day slower, from the perspective of the ground, then from the perspective of the satellite, the ground would also be running 7,000 nanoseconds per day slower. Now from the ground, we can do a pre-launch adjustment, and instead of doing the full 45,000 nanoseconds, we can do the 38, which was the net change that we talked about earlier. So in essence, if we started with 45 and then backed it to 38, that would be like speeding up the clock by 7,000 nanoseconds per day. From the perspective of the ground, that will do the trick because, again, with this velocity imparted, it's suddenly traveling 7,000 nanoseconds per day slower. But because we speed it up by 7,000 nanoseconds per day, now the ground reads the satellite is running in sync with itself because not only gravity, but the velocity has also been compensated for. Both have been compensated for perfectly. The magic number is 38,000. And from the perspective of the ground, the satellite is now running in sync with the ground. The problem is from the perspective of the satellite, the ground was already running out of sync. Okay, the ground, and if we take the full 7,000 and say that this is relative motion from the perspective of the satellite, if we take the full 7,000, we can say, well, the ground was already running 7,000 too slow, and by us speeding up the satellite clock, now the satellite clock could actually see the ground running 14,000 too slow because changing the speed of the clock would actually be a mechanical thing that you're going to do before the launch, and that will give you an equal but opposite effect. So without the adjustment, the satellite would see the ground is running 7,000 slower, but we tamper with the clock some more before we launch it, and we speed it up, which now this sped up clock will actually see the ground clock running even slower. So the moral of the story is if we need the satellite and the ground to be synced two ways simultaneously, the entirety of Einstein's special relativity actually prevents that from happening. So we would either have to abandon that part of special relativity and say that only the moving clock is running slower as a consequence of its velocity, and that moving clock doesn't also see the earthbound clock running slower as a consequence of its velocity. And then all effects, whether it's gravity, velocity, simulated gravity, rotational motion, or whatever, all effects would be equal but opposite, and therefore would be able to be compensated for. It's my contention that that's probably what's happening, because if we have any kind of relative motion between the two, whether a lot or a little, then there's no way we can adjust for the relative motion between the two clocks in the two different positions, because again, you send it one way and it's going to actually throw the other direction out of whack even more. Okay. So anyway, in 2008, that was the my vision of the theory that I wrote about, and essentially I did just that. I treated all of this as relative motion, not only from the perspective of the ground, but the satellite that was in motion. I said that the satellite would also see the ground in relative motion, even though it was the one that was moving. This is a circular example, so it's a little different than going all the way back to Galileo's principle. But if you think about some of the implications of Galileo's original principle, I could be riding in an automobile down the road, and if I'm going at constant velocity, I can't claim that I have absolute velocity. I can say, literally, that the entire planet Earth and the rest of the universe is moving underneath my feet, and I'm the one who's perfectly still, and everything else is in motion. I can actually claim that legitimately, because there is no absolute motion, there's only relative motion. What I did was I just translated that to this circular motion here. And I actually got some criticisms. The article that I wrote, I sent out to a lot of different people. Some people read it, some people didn't. A physicist or two had a problem with this, because they said that, and you know, this goes back to what people like Albert Einstein and Wolfgang Pauli and a lot of other folks wrote conventionally about this theory, was they were saying that since the satellite isn't in inertial motion, because it's in a constant state of direction change, that I can't claim that from the perspective of the satellite, we could look at this as relative motion from the perspective of the satellite on the Earth. And in order to answer that criticism, we should really go back and take a look at what Einstein said in 1911, and how he said that gravitational potential, whether it's real gravity or simulated gravity, how that will affect time dilation. And I've got a couple of equations here, and just this symbol, it means gravitational potential, so anytime we see that, and that's the thing that when divided by the speed of light squared is the calculation for the extent of your time dilation. So the higher your gravitational potential when divided by the speed of light squared, the bigger discrepancy you're going to get in how the clocks elapse. Okay. Gravitational potential can be applied to a lot of different simulated gravities. In linear acceleration, like our elevator box could be floating out in outer space. All of a sudden, the rocket accelerates it in a certain direction, but it's linear. And the gravitational potential would be the rate of acceleration would be the g-force that would be equivalent to. So we can use A for acceleration or G for gravity, either one that you like. And the h would basically be the height or the distance between the two things that are measured. In our case, we had the floor of the elevator and the ceiling of the elevator, but we could make our theoretical elevator as long as we wanted to. We could have an elevator that's 8 feet high, or we could have an elevator that's as long as the Empire State Building being dragged in outer space. And if it's accelerated, we could look at the time differences between the two clocks from one end to the other based on what is the extent of the g-force, in other words, how much is it accelerating, and what is the distance between those two, okay? Those two things together will give us our gravitational potential. So as you can see, multiple things can contribute to a higher gravitational potential. In real gravity, we have the g, which is a gravitational constant, multiplied by big M, which would be the mass of, in this case, the Earth, if we're talking about on Earth, and then the radius. So in real gravity, the radius would get larger the farther we get away from the center of the Earth. So in this particular case, we would have differences in gravitational potential between something on the surface of the Earth and something that's 11,000 miles off of the surface of the Earth as with these rotating satellites. So because we would have different values here, then each of these would have different gravitational potentials, and we would therefore have different time dilation values for each of these. And that is pretty much the explanation for why a clock, a stationary clock that's 11,000 miles up that isn't moving, again, we'd have to magically hold it still, why that would be 45,000 nanoseconds faster than the clock on the surface of the Earth, because they would have different gravitational potentials, because these values would be different for this equation in real gravity. Excuse me. Our third example would be the gravitational potential as a consequence of a rotating frame. Well, we kind of sort of have a rotating frame. We have a satellite in orbit. It's not a complete rotating frame. It's not like a record on a turntable or a person on a merry-go-round with a flat circular platform. You can walk inward or outward while the platform is still moving, although I wouldn't recommend it. But in that particular case, you've got an entire frame that's rotating. In this case, you've kind of got the edge of the frame that's rotating, and anything that's not actually on the satellite is off of the rotating frame. But in any event, this would be the equation that would be argued, that would be used instead of looking at this as constant velocity and inertial motion from the case of both parts. So what we have here is a gravitational potential using up this. Well, what is this? This is omega squared times r squared, which would actually be a angular velocity. Going back to the turntable example, although we always use CDs and iPods now, but in the old days when you put a record on the turntable, you could put it set it at various speeds, and that rotating frame, you could put something on the end of the record, like maybe a penny, and depending on how fast it went, the penny might fly off of the turntable. So that penny would actually be sent to the edge. Another example is a centrifuge, or even better yet, one of those rides at the state fair where you get on it and everybody kind of gets strapped in to the outside, and the thing starts spinning, and they can feel themselves pressed up against the metal cage as the thing is spinning around at high speed. That is a form of simulated gravity, but it's a circular acceleration. But so in this particular case, some would argue that this would apply to this because we're dealing with something in a rotating frame that is not inertial. Now, the interesting thing is we can actually convert this angular velocity squared and this radius squared to a real velocity value. And since this is the gravitational potential, and in order to solve for the time dilation, the gravitational potential would be put over the speed of light squared, then the gravitational potential with the speed of light squared in this rotating frame would start out as that, but since the w squared r squared could be converted to a standard velocity over 2c squared, that actually is the same as a simplified equation for constant velocity. So essentially what we have here is, what many have argued is that when you are in this rotating frame and this equation is equivalent to your gravitational potential, it will actually produce a time dilation that is the same as what you would get if you were in constant velocity. Well, that's nice and convenient, because that would be a way for those to measure from the perspective of the satellite how the clocks speed up or slow down on the surface of the Earth based on this equation. And if this winds up reducing to essentially the same equation that you would get for the constant velocity, then according to them, there wouldn't be any discrepancy. Okay? Okay, so anyways, to answer my criticisms, and by the way, interestingly enough, any criticisms that I got with using the constant velocity in both directions, even though this technically isn't inertial, none of the criticisms provided an actual mathematical argument or a detailed argument as to what the answer would be. So I figured I would make the best possible argument for these folks. And that's exactly what the argument would be.